So with that, I am pleased to welcome our next speaker, Klaus Lackner.
Hello, thanks for having me, and thank you, Stan. You really set me up nicely with your introduction because it perfectly dovetails with what I want to say. I'll start out with pointing out I'm on the older end of the spectrum here, and I've been at it for a while. Nearly 3 decades I have been worrying about how to do carbon management and what that actually means. I think in a nutshell, it means we create fugitive carbon because we dig it up from under the ground and we combust it and we produce CO2 we happily let out in the atmosphere and then don't worry about it anymore. And I think in the future, there is a dire need to capture and remove that fugitive carbon by one way or another. And yes, it is all hands on deck. And I think one of the important things to not forget as we talk about direct air capture is that biological systems, plants, have been able to do this for a very long time. So we should take advantage of that fact. On the other hand, the amounts we are producing are simply too much for biology. We would need to put far more trees up than we can really put up. And in retrospect, in hindsight, it's not all that hard to see, because our problem is not so much that we cut down trees, but we burned a lot of coal, oil, and gas, and we can't actually grow quite enough trees to make it work. So in the end, we have to figure out how to get carbon out of the environment with going beyond just what biological systems can do. And this is where direct air capture comes in. In many ways, I see this carbon problem as a waste management problem. We are dumping carbon into the atmosphere. We just let it run away and it goes wherever it wants to do. And the excess carbon in the environment is piling up and is becoming a real problem. So just like with sewage, just like with garbage, we have to start thinking about how to solve the problem. And by the way, it's sort of obvious that this is different than just mitigation. If you think about it for a moment, if I left my garbage on your front doorstep, you wouldn't consider it an advantage that it's 10% less than last year. We really will have to figure out how to balance the carbon budget and put every carbon away we dug up in the first place. Of course, that also creates an enormous opportunity for reuse and recycle. If it costs you money to get rid of the stuff, you have to pay for getting rid of your garbage. If you could reuse it, recycle it, and do it again, that would be a good thing to have. So direct air capture goes with storage. You can call that direct air capture at CCS. And you do that while you're phasing out fossil fuels, which will take us some decades because we will need to keep energy stable in the system, and we need to allow developing countries to grow. Otherwise, they cannot stabilize their economies. And ultimately, direct air capture can produce the carbon. This is the air mining part for fuel production, for energy storage, and for something useful, right? And I think the really new opportunity which is coming in here is that renewable energy is getting very, very cheap. Raw electricity from a photovoltaic panel today is much cheaper than electricity from coal. Its downside is it's intermittent, right? So we have to figure out how to interface with this intermittent source of energy, which is gradually approaching the raw cost of natural gas, as a matter of fact. And we need to figure out what to do with the excess, which we will have at some point. Batteries will store it for hours, but ultimately, if we want to deal with seasonal storage and dealing with the last 20% of energy consumption, which really relies on liquid fuels, think airplanes, think ships, you want to convert that stuff to fuel. And you can do that if you have access to the CO2. You mine the carbon from the air, convert it into fuel, which ends up back in the air. You take it back out and close the cycle. As you do that, you can also replace all the petrochemicals and move forward that way. You can do this with the cheap stuff, which allows you to put vast amounts of carbon away. And you can do it with the expensive stuff, where in the early days you have a competitive edge, but it's very unlikely that people will pay hundreds and hundreds of dollars to put tons and tons of CO2 away because it's going to get too expensive. So in the end, you need a number of enabling technologies. You need storage. I think we are past the point where we can sort of waffle and say, okay, we just stop emitting and we'll be fine. If we stopped today, we might be arguing about 50 ppm. By the time we actually put the brakes on the car and we stopped it, we very likely are having a 100 ppm mismatch. And we can argue what that really means. I suspect we very likely end up coming back from 500 to 400, but we may equally well come back from 450 to 350. And keep in mind, by now, we are parts per million in the atmosphere. We are by now at 415 parts per million, and we're going up 5 ppm every 2 years. So we are not all that far. We are about 15 years away from running over that line in the sand, which is probably above the 1.5 degree warming. So we need these options, and we need photovoltaic energy. We need to make it cheap so that we actually can link it all together and not worry about having only the wrong kind of fossil energy. And we gradually have to replace all fossil energy in this process. We need some way of converting that electricity into chemistry. Probably electrolysis, but something else might come in equally handy. And then, of course, you need direct air capture, which is something I've been working on by now for 2 decades. And direct air capture is technically feasible. Let me stress that. There is no thermodynamic concern. If you work out the thermodynamics of separating CO2 from air, you need to pay 22 kilojoules per mole. When you made 1 mole of CO2 by burning gasoline, you just got 700. So the thermodynamic boundary is not all that hard. What people have argued correctly is that if Sherwood's rule applies, then we are in trouble, because if you're really 300 times as expensive as flue gas scrubbing, then we are dead on arrival. So we have to figure out how to beat Sherwood's rule. We think we have figured it out, mainly by being passive. If you look at why Sherwood's rule usually applies, it's the first step in the process. Think of mining ore for metal. The first step in the cost process soaks up all your cost. So the important part is that air capture cannot cost all that much money in contacting the air. The cost has to be in extracting the CO2 from it and then reproduce it as pure CO2. In a way, what got me started was the observation, if wind is good, DAC is better. And what I mean by that is, if you have a cubic kilometer of air and you're willing to pay 5 cents a kilowatt hour for kinetic energy, you have $300 worth of kinetic energy in that cubic meter of air, assuming it moves at 6 meters a second. If you ask, I'm willing to pay a tipping fee of $30 a ton of CO2, how much CO2 is in that cubic kilometer of air? It's $21,000 worth. So in a way, the CO2 concentration in the atmosphere by this measure is 70 times larger than the wind energy. Yet nobody argues we can't do wind energy. So therefore, I am very confident that the front step of touching the air and getting the CO2 out is affordable. The big question is the second step of prying the CO2 loose from the sorbent affordable? We believe we can do this. We have a number of ways of doing this. We are not the only ones. And that is not much more expensive than at a power plant. So therefore, my prediction, if the power plants do it as well as they can possibly do, they will be a little cheaper than we, but they will not be 300 times cheaper. They will be 1.5 times ours. And we can go after airplanes. We can go after CO2 that's already in the air. Ultimately, direct air capture sets the price of carbon. Because if you have a more expensive way of getting your carbon back, by all means do air capture. If you have a cheaper way of doing it, by all means do that first. You are left with that last 20%, which comes from airplanes and other places where it's very, very hard to avoid putting the CO2 into the atmosphere. And you are left with all the emissions you already did in the past, and you have no better way of doing it. So we at ASU are working with a brand new startup, a European startup, which calls itself Silicon Kingdom Holdings, and they have started to hopefully build prototypes in the near future. So we, just like other groups are now in the game of trying to actually find places to do this, and ultimately this comes down to the cost of carbon. I would make one other point last before I finish. If you look at the cost of photovoltaics, it has gotten 100 times cheaper over the last 40, 50 years. As a rough rule of thumb, every time you doubled, the cost dropped 20%. And in order to get from kilowatts to gigawatts, photovoltaics had to grow millionfold. And that doubling rule roughly says that every time you grow 1,000-fold, your cost comes down tenfold. I'm not making a prediction that air capture can do that as long and as hard, but I also point out it doesn't. If you look at, for example, Climeworks, they actually right now can collect CO2 at about $500 a ton. If they were 10 times cheaper, they would be really in the middle of things. Based on this rule of thumb, which is true for mass manufacturing, costs should come down tenfold if you grow from kilotons a year, which is where we maybe optimistically are today, to megatons. At megatons, you are just serving industrial markets for CO2. At the end of the day, you have to go to gigatons. Whether you can get another factor 10, I don't know. Nobody knows, because they are at the end costs you cannot squeeze down. But that you can get the first factor of 10, I am very, very optimistic on. And that is learning, and it is learning which has been demonstrated by wind energy. It has been demonstrated by photovoltaics. It has been, by the way, demonstrated by car engines. If you look at a car engine, it is 100 times cheaper than a power plant, kilowatt for kilowatt. And that is the case because they drove costs down relentlessly by pushing on it very, very hard by mass producing. And so you can get these factors, not just for computers and disks and that kind of stuff. You can get it for old-fashioned hardware as well, if you're willing to go the mass production route. So I'm actually very optimistic that direct air capture systems will look small in individual units, but create large, large, large fields. If you have a ton a day, I think we can squeeze this into a shipping container, and 100 million of those shipping containers could collect as much CO2 as the world is currently emitting. We have 1 billion cars on the streets, on the roads. So therefore, going to 100 million may sound formidable, but it is well within our industrial capacity to do that. As a matter of fact, we would have to build 10 million a year if these things last 10 years, and the production of cars grew by more than 10 million a year over the last decade. So we can get to industries on that scale. As a matter of fact, to come to the shipping containers, Shanghai Harbor alone is shipping out 30 million containers a year, which tells you there's an industrial capacity right behind Shanghai, which is 3 times bigger than what the world would need to solve the world's climate problem. So can we do it? Can I give you a guarantee? The answer is no. I can pretty much give you a guarantee if we fail that things will get very uncomfortable. And I leave it at that, and I'd be happy to answer questions.
Wonderful, thank you, Klaus. I think you and Kim Stanley Robinson as the first 2 speakers, I think really shared such a clear vision for this idea that we need all hands on deck. This is economic, it's technological, and it's social. And there's so much that we need to acknowledge that we don't know. And I heard that come up in your introduction as well. So we had some great questions from the audience. By the way, if you're not on Slack, you can look in your email for an invitation over the last couple of days to join the AirMiners conference Slack group. And that's where you can find the opportunity to ask questions to Dr. Lackner right now. But in terms of, one of the questions that came in was in terms of thinking about storage of carbon dioxide removed through direct air capture. In terms of like maybe a pie chart, or how do you think the majority, looking 10, 50, 100 years out, how do you think the bulk of carbon dioxide removed from direct air capture, what do you think is going to happen to it? Is it
well, I'm of course prejudiced, right? Because in the 1994 timeframe, we wrote a paper where we said the safest way of getting rid of CO2 is to make a carbonate out of it. And so my hope would be that that's the long-term answer. I would argue too, we have a 50-year time problem right now. So I'm willing to look at any option which stores carbon for 50 years, and I'd be happy to try to do it a second time if we need to. But having said that, I see that the oil companies, by injecting CO2 underground in saline aquifers like you see in Sleipner, claim to have vast capacity. We can argue whether this is really true, but I think what is certainly true is that for the next decade or two, we don't have the excuse we don't know where to put it. Now, we may run out, but in the short term, we are not going to run out. The second option I am really excited about is CarbFix in Iceland. I had helped get that started. I have not been part of it. What I think is exciting about it is it does mineralize the carbon. It makes carbonates out of it underground. It offers a potential of being very large. They still have to prove that. It is conceivable that the fraction of basalt which reacts is so tiny that it doesn't really work on a large scale, but I think everything points the other way, that they actually have the capacity. Keep in mind what you're watching here is the Mid-Atlantic Rift, and you need lots of water. And if you follow the Mid-Atlantic Rift underwater, you have plenty of water, and you can go all the way to the South Atlantic and you're still in the same geological formation. So I expect that this alone has far more capacity than we ever need, and it would be permanent. So I believe we don't have the excuse of saying, we really don't know how to do that. There may be many different competing forms. People have a tendency to look for the cheap ones and then worry about 20 years later that they were permanent. But overall, we have plenty of options to put far more carbon away than we ever took out of the ground. It will come at a price. Right? Waste management is not free. On the other hand, it solves very important problems. I am skeptical that the demand for carbon is just going to be so high that we solve the problem that way. We produce more CO2 than we produce gravel and sand. Just let's be very clear, that is the scale. Right? So therefore, I think some of it is a disposal problem until we figured out how to not use the stuff anymore. But I think the capacity to do that exists.
Beautiful. I love the kind of sharp rationality of the way that you present this. Like so many of the other people that we're having speak today, I think that Klaus, you have a great way of talking to both the theoretical, the numbers, but also look, there's no excuse for you getting stuck in a 50-year vision when we have this solved. This isn't a limitation over the next year, over the next 10 years. One of the questions that came in was around, I think that a lot of times, myself included, we tend to think like, okay, direct air capture it's being taken care of by the direct air capture folks, and we can all kind of build an ecosystem downstream from that. But one of the questions that came in was around direct air capture. So from a technology standpoint, what are you most excited about specifically with the technologies to grab onto molecules of carbon dioxide out of the atmosphere?
Well, I mean, there's plenty of sorbent technology, right? So we have by now a good number of sorbents. Personally, I'm very excited about these moisture swing sorbents, which allow you to use water to drive off the CO2 rather than energy. Of course, then you become a water consumer, and we have to figure out which one's more expensive than the other. We have figured out in the meantime ways of being sort of hybrid. where the water is expensive, we keep it. Where the water is cheap, we use it. And if we keep the water, then we better pay with energy, because there is no such thing as a free lunch. But there are plenty of other sorbents. I am particularly interested in passive designs, because this goes to the Sherwood rule. To give you a funny analogy, uranium in seawater was considered a really good source of uranium, but it's 3 parts per billion. So in the 1960s, people said, we have some resins, we can soak the CO2, the uranium out of seawater. We have some resins to
now playing Sleep Like a Baby Tonight by U2.
I don't know what's happened here. I woke Siri up. I apologize. I don't know how that happened. I woke Siri up and she starts to play music. So to come back to the uranium, so they said we have a resin to absorb that, and we can make this work. And Sherwood's ugly rule asserted itself and said, well, this resin stuff worked really fine, but the energy you needed to pump all that water through filters is killing you. And then in the 2000s, the Japanese group said, well, we don't need to pay that. We can make these resins as strands which look like kelp, and they sort of float in the water, and we anchor the bottom to the ocean floor between 2 islands, and we let the current take care of it. And then 6 months later, we harvest the resin, and lo and behold, they got nearly competitive with ordinary uranium. The point is, they beat the socks off Sherwood's rule because they took that first step, the contacting step, and made it exceedingly cheap, right? So that's what we do in air capture. We stand here, and I currently got into an argument about methane capture from the air. And I said, if you use pumps and blowers to drive the air through to get the methane out, which is 100 times less concentrated, you are not going to make it. You have to be passive. You have to let the wind bring the stuff to you, not the other way around. In methane, you have also the problem that in 10 years it goes away by itself. So you better be faster than that. Otherwise, you didn't make any difference. But that's a side issue. Right? But the overall story is passive designs, I think, are the ones which take the Sherwood argument off the table and thereby allow you to get to the really low costs. And then clever sorbents for clever areas. I think ultimately you need to be able to do this in any part of the world. And our moisture swing is really good in a dry climate. It's lousy in a wet climate, in a tropical climate. And ultimately, I would like to do it in Alaska and everywhere. Wherever there is a good use or sink for the carbon, we need to be able to run. So that's my challenge and my excitement about this.
Beautiful, thank you. Thank you, that's a great answer. I think it sparked, as you can imagine, even more questions. I think that we've got some questions around utilization, and I think it starts to introduce something that Stan brought up earlier around the economics. So when you think about storing carbon underground, this is something we talked about the other day, Klaus, but could you share a bit about how you see that working profitably, and yeah, just your vision on the economics?
Let me start with, there's a company by the name of Waste Management, which happens to operate in the area I live, and I pay them money, right? I could hire a competitor, but I don't have the choice not to pay, right? Because we all have agreed that leaving the garbage in the front yard or the sewage in the gutter is not a good idea anymore. We learned this in the 19th century, and so there are services which sprang up around us. In some places, it's run by the local government. In other places, like here, it's a private company. But either way, I, as the consumer, end up paying for it. I would argue the simple rule which can get you to fix the carbon problem is to say, if you add to the carbon pile, if you create more mobile carbon, which then is fugitive in the environment, you got to figure out, you need to show me that an equal amount of carbon has been sequestered. So I would argue if you bring up coal, oil, or gas to the surface, you better have a certificate of sequestration, which has been generated somewhere else or in your outfit, right, to match what you just brought up. then you didn't change the carbon balance, and the carbon which you brought in is now properly part of the mobile carbon pool. Now, that will get you to zero balance long before you manage to stop fossil fuels. And it will cost money because people will have to pay for the certificate, just like I have to pay for my garbage, right? Because I'm paying money for this certificate, photovoltaics, making synthetic fuels will look a little better, right? And it will compete with that. I would argue in a world which takes up some of these certificates and tears them up because they don't want to be used for additional fossil carbon, but they are removing the old sins, take care of the old carbon, which is already in the atmosphere. A world which wants to come down 100 ppm has to find storage for 1,500 gigatons of CO2. In that world, certificates won't get cheap because I don't have to work hard to convince you to buy it. So you will pay whatever the going price is. As a result, this will really drive you to renewable energy. And so I see us moving away from needing these certificates because we have an alternative which is cheaper. Right? But in order to build it, I think the first rule has to be, if you create garbage, you better clean it up. And right now we are doing it backwards in my mind. There's nothing wrong with saying you need to reduce your emissions. You need to make less CO2. There's nothing wrong with saying you should recycle it. And there's nothing wrong with saying you need to reduce it. All of these things are very good. But when you get to the point where you have failed on those things, you are not allowed, you shouldn't be allowed to say, okay, I couldn't do it, so therefore I'm just allowed to put it in the atmosphere. At that point, the system has to balance. So I would start from, first and foremost, you're not allowed to put anything in, dump the stuff in the atmosphere. The simplest way of making that balance is if you bring in fresh stuff, you better show me a certificate of sequestration, which has put it away. Then you can say, given that I now had to pay good money to get rid of it, I should figure out how to recycle it. And suddenly, synthetic fuels will look much more interesting than they do today. The problem you have now is that, yes, CO2 from the air might be very valuable, but a lump of coal is a cheaper way of getting that coal. Right? With that certificate of sequestration, I tip the balance in the right direction.
That's exactly right. So when you say I take this certificate of sequestration or I create it, one question that's come up is kind of more downstream. It's around carbon utilization, making products, making things like fuels, making building materials, making a pair of shoes. How do you think about those types of uses in this framework?
Well, in this framework, you need to create a certificate of sequestration. And I would argue that takes three things. It takes, first, you have to show me the box you put the carbon in. Could be an underground reservoir, could be a forest, right? Secondly, you have to show me that you actually put the carbon in. Thirdly, you have to show me the carbon is still there, right? And that, in some sense, is the hardest part. And then there's a corollary. If you lose it, you have to buy a new certificate of sequestration to make up for the fact that you lost it. Right? If you do all of that, we can now look at the shoes. Do you really want to bother to count all the shoes and deal with that and get a certificate of sequestration, which once the shoes are worn out, is not useful anymore? Now with my house, I might consider that all the lumber in the house is worth a certificate, and I have a few $1,000s riding on my home as certificate of sequestration, which I know that when I sell the house, I have to give back. Or when the house burns down, that's part of my insurance. Right? Because I liberated the carbon again, right? So you have to now ask this for every single application, whether it's worth your time. But if you look at synthetic fuels, I would argue most likely you're not going to play. But you get a real advantage of the fact that your competitor had to buy one, right? So your synthetic fuel made from PV is free of that certificate because the carbon in there was mobile to begin with. The carbon from the petroleum you had to mobilize, and that mobilization costs you a certificate of sequestration. And if they run $50 a ton, they are running, I think, $15 a barrel. It's 50 times 0.4, so it's $20 a barrel, right? So that's the extra price you have to pay for oil. The big question now is, can I compete with that? And my guess is photovoltaics is getting cheap enough that the answer to this question is yes. So I see us getting very cheap electrolyzers in the desert, converting CO2 from the air and water into hydrogen and CO, which then is turned into your fuel of choice, which I think in the short run is natural gas and gasoline because we have the infrastructure to deal with it. In the long run, it may be methanol or dimethyl ether because those are smarter, but the markets can figure that out. And at that point, we don't need fossil fuels anymore. And what I really like about CloudFix is it doesn't need fossil fuels. Nearly all of the other discussions about reducing carbon ultimately require the cooperation of the producers of the pollution. Right? The coal plants need to figure out how to put a scrubber on. The gas-fired power plants need to put the scrubber on. Right? All of these things have require the cooperation of somebody who finds this distasteful and economically a burden, right? If you talk to the oil companies, they tell you we can put a lot of CO2 away because we have the technology. But again, they view this more as a burden than a help. CloudFix is run by basically hydrologists, people who don't really make CO2. And air capture is not directly tied to this either. So I actually think by coming in from the outside, you can actually overcome this moral hazard thing and turn it on its head. Because what you are going to say, if I can do this for $80 a ton, that fossil power plant will say, well, you know, it's so difficult to do that. But then you say, well, you don't have to do it for $80 a ton. You just have to buy it. And then you'd be surprised how fast they figure out that they can do it at 70. But as long as you don't have somebody there who says, I can do it at 80, so you don't have to do it, they will tell you how nearly impossible it is to get this below 100, and that they need lots of time and research to make that happen. So I actually think the presence of direct air capture, which decouples you from the polluters, actually could accelerate the process rather than decelerate it, because it creates a competitor who has an incentive to make it happen, rather than having somebody who would like to delay that as much as possible. Because as long as you don't have to do it, life is better from the point of view of the fossil fuel producer.
I love it. Thank you, Klaus. I really appreciate your perspective on all this. One thing that I've always noticed is that you have a very clear framework that it seems like you always have in your thinking. For the rest of us who are in the audience, do you have any recommendations for a book or some resource to get better at this kind of structured thinking?
I don't know. There's a book, Fixing Climate, by Wally Broker, and I thought that was very nice, but he's bragging about me, so that's not fair.
Okay, terrific. And then
but overall, I don't think it's an accident that some of the biggest players in direct air capture came out of physics, because they train you to think this way. Peter Eisenberger is a physicist, David Keith is a physicist, I'm a physicist. I think it's training you come with to think in big boxes and put control boxes around it, which nearly sounds like chemical engineering, but what convinced me very early on, there's a finite amount of carbon in the environment, and it takes thousands and thousands of years, about 100,000 years, for that carbon to get out again if we put too much in. And so it didn't take rocket science, as far as I'm concerned, that sometime in the 21st century, we will have to be carbon neutral. And I think what we learned by now is that we will have to be carbon neutral at a level which is lower than where we will end up.
Well said. Thank you, Klaus. Thank you again for sharing all this perspective. I think everybody join me in saying thank you. Lots of thumbs up I'm seeing in the screen, and claps and things like that. And we appreciate the musical interlude as well.
I apologize. By the way, it's still running. I just put the volume to nearly zero. This never ever happens. But Siri just woke up and heard what I said and decided that I wanted music.
Beautiful, awesome. Well, I hope that everybody continues to think about this. I'm sure you can get in touch with Klaus if you like.